This is the video for section 13-4 in accelerated geometry, where we're going to be talking about graphs of rational functions. So the essential question for this section is, what is the visual representation of a rational function? We will have 5 vocabulary words. They are continuous function, discontinuous function, hole in a graph, hyperbola, and rational function. So we're going to jump right in with some vocabulary. And what you should already know from studying in this unit, a rational function is a function that can be written as a ratio of 2 polynomials. Up until this point, we have been spending the entire unit talking about rational expressions. So the only difference between an expression and a function is that you write them as y equals, or f of x equals, or g of x equals, or whatever you want to call it. So for example, y equals 2 over x minus 4 would be a rational function, or f of x equals x plus 3 over x squared minus 4x plus 7. Those are both rational functions. The parent graph for all rational functions is y equals 1 over x. Its graph is a hyperbola, which has 2 separate branches, so it's almost like 2 parabolas, kind of. The graph of every rational function does not necessarily look like a hyperbola, but 1 over x happens to. The graphs of rational functions may also contain holes, horizontal asymptotes, and vertical asymptotes. This graph right here is the graph of y equals 1 over x. So you will see that it has 2 separate branches that are parabolic. It happens to have a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. It does not have any holes. So once again, not all rational functions are going to have graphs that look like this, that have the 2 separate branches. They may have 3 separate branches, they may only have 1, they may look like a straight line but have a hole in them. So do not assume that all rational functions look like this. But the most basic of all rational functions, y equals 1 over x, does look like this. So the first thing that we're going to talk about is transformations of rational functions. So you can take the graph f of x equals 1 over x and you can transform it the same way that we've transformed lots of other types of functions over the last several years. You can take, instead of 1 over x, you could put some sort of constant up in the numerator. That constant a is going to represent a vertical stretch or a compression by whatever factor a is. So for example, if that was a 2, then we would be stretching all of our points vertically by 2. If this constant right here is negative, then that means that the negative part of it, just like all negatives in all of your transformation functions, represent a reflection across the x-axis. We can also combine a number down in the denominator here, and we would write it as x minus h. That number down in the denominator represents a horizontal translation. It's to the left for h is less than 0, and to the right for h is greater than 0. So for example, if this was an x plus 3 right here, that would be a horizontal translation, left 3. We do the opposite because of that minus sign right there. And then outside of the rational expression, you could have plus or minus another constant, and that value k represents a vertical translation, and we do exactly what it says. So if this was a plus 4, then we would take our entire graph and we would shift it up 4. So using that information, and using f of x equals 1 over x as a guide, we want to describe what the transformations would be to 1 over x in order to achieve this g of x function. So for number 1 here, we have g of x is equal to 1 over x plus 2. So if you compare this to f of x, the only new addition is this plus 2 in the denominator. So if you remember, if it's added or subtracted in the denominator, then that is a horizontal translation. And we do the opposite of what it says, so that would be a translation left 2. So that means that everything translates to the left 2. The horizontal and vertical asymptotes go to the left 2. So I would have a vertical asymptote, instead of at x equals 0, it's now at x equals negative 2. Now the horizontal asymptote sliding it left 2 doesn't change anything. It's still y equals 0. Some other important points that we usually have in the graph of y equals 1 over x is it typically goes through the point 1, 1. So, through 0, 1. So that has now, through 1, 1. I'm on cold medicine, can you tell? So if we shift that left 2, we would now have an important point at negative 1, positive 1. We also typically have a point at negative 1, negative 1. So if that shifts left 2, it is now at negative 3, negative 1. Those 2 points right there are enough for us to get an idea, and I am not very good at drawing these on my airliner here, but you would get an idea of the 2 branches that you are to draw for your hyperbola for this function. And you do not want to cross over those asymptotes. So based on what we did there, I want you to pause the video for a minute and see if you can describe the transformations from f of x to g of x for number 2 and draw what that graph would look like. Okay, so I don't know about you, but I saw that since we had a number outside of here that the transformation was down 3. So that did not affect my usual vertical asymptote at x equals 0, but it did affect my horizontal asymptote of y equals 0. That slid down and is now at y equals negative 3. I also took those 2 important points of 1, 1 and negative 1, negative 1 and slid both of those down 3 to have an important point at 1, negative 2 and negative 1, negative 4. And then using those 2, I was able to draw the 2 branches of my hyperbola. Okay, so that's most of the transformations we're going to do are pretty basic there. But the important stuff we're going to get into are the actual components of all rational function graphs. And we're going to start with talking about the vertical and the horizontal asymptotes. So for a rational function that's in the form a over x minus h plus k, the graph will always look like a hyperbola, like the 3 that we've done so far. The vertical asymptote would be the line x equals whatever this h value is. And so the domain restriction would be x such that x does not equal whatever that number is. And we'll talk about y in just a minute. And then you would have a horizontal asymptote at the line y equals k, so whatever that k value is, and your range would be y such that y cannot equal whatever that k value is. So for example here on number 3, if I wanted to determine the asymptotes, the domain, and the range of this particular function, I know that I would have a vertical asymptote at x equals negative 3, and I would have a horizontal asymptote at y equals negative 2. My domain would then be x such that x does not equal negative 3. So wherever you have a vertical asymptote, you also have a domain restriction. And wherever you have a horizontal asymptote, you also have a range restriction. So your range is y such that y does not equal negative 2. Now you do not have to write the notation this way for domain and range. You could write all real numbers except for negative 3, or all real numbers except for negative 2, or you could just write x cannot equal negative 3 and y cannot equal negative 2. I typically write it as all real numbers not equal to negative 3 and all real numbers not equal to negative 2. But as long as you get the point across as to what particular points cannot be included in the domain and the range, your answer should be acceptable, unless it's completely ridiculous the way that you wrote it. Okay, so pause the video again, and I want you to give number 4 a try. Find the asymptotes, the domain, and the range. Okay, so I got a vertical asymptote at x equals 3, a horizontal asymptote at y equals negative 5. The domain is all real numbers where x cannot equal 3, and the range is all real numbers where x cannot equal, or where y cannot equal negative 5. All right, so that completely wraps up transformations. So a discontinuous function is a function whose graph has one or more gaps or breaks in it, which makes sense. It's not continuously drawn. If you were to trace it with your pencil, you would have to lift your pencil up to continue drawing the function. These functions include rational functions. A continuous function is a function whose graph has no gaps or breaks in it. So you would never have to pick your pencil up if you were tracing the graph of this function. So these functions include linear, quadratic, polynomial, exponential, and logarithmic functions. They are all continuous. But we're focusing on rational functions in this section, so we're talking about discontinuities. And those discontinuities include any place that you have asymptotes, vertical or horizontal asymptotes. So we're going to focus right now on zeros and vertical asymptotes. If you have a rational function f of x and it's represented by one polynomial function over another polynomial function in standard form with no common factors other than 1, so that means that all of the factors that they do not have in common, then your function is going to have zeros everywhere that the numerator equals 0, and it's going to have vertical asymptotes everywhere that the denominator equals 0. Now, let me make a point about that. It's only about the factors that they don't have in common. So, for example, if I had f of x equals x squared minus 4 over x squared plus x minus 2, this will factor to x plus 2 times x minus 2 over x plus 2 times x minus 1. So when I'm trying to find the zeros and the vertical asymptotes, I only focus on the factors that they do not have in common. So my zeros would occur where the numerator factors, so that would be x minus 2, is equal to 0. So I would have a 0 at x equals 2. My vertical asymptotes will occur where just the denominator factors are equal to 0. So I would have a vertical asymptote at x equals 1. So you only pay attention to the factors that they do not have in common. The factor that they have in common is going to create what's known as a hole, and we will talk more about those as we get further along in the video. But I wanted to make that very clear that it's the factors that they do not have in common are what create the zeros and the vertical asymptotes. So in number 5 here, I want you to try to find the zeros and the vertical asymptotes of this rational function and try to give it the best shot that you can to graph that function. Okay, so I factored out the numerator on number 5 and had x plus 4 times x minus 1. So you'll notice there are no common factors. So that means that both of the factors in the numerator create my zeros. So I set both of those equal to 0 and figured out that I have zeros at negative 4 and positive 1. So you'll see over here in red that I went ahead and put those on my x-axis there. And then your vertical asymptotes are going to come from the denominator, so x plus 3 equals 0, so I knew that I had a vertical asymptote at x equals negative 3. So I drew that on there. Now, as to how my curves were supposed to be drawn, I really couldn't look at my equation for my function and figure that out, and the 2 zeros and the vertical asymptote didn't really help me a lot. So what you would want to do at this point to try to estimate your curves is just go straight to your calculator. So I went to y equals, and I typed my function in, not in factored form, I typed it in straight how it was at the beginning. Notice you do have to put parentheses around the numerator and parentheses around the denominator. And then I hit zoom 6 to get my graph. So now I have an idea of what my graph should look like, and you'll see that it does cross through positive 1 and negative 4. And unless you have an older calculator, your calculator will not draw the vertical asymptotes for you. But that gave me an idea for how to draw my curves, and you'll see I'm not so great at drawing the curves. So this brings me to an important point. When you have a problem where you have to show the zeros and show the vertical asymptotes on a graph, or the horizontal asymptotes, or the holes when we get to those, you have to show the work by hand for how you figured that out, and you have to actually highlight them on your graph. Like, I can see these zeros, and I can see this vertical asymptote, and then I just sort of drew my curves in. We are going to be looking for those specific things on your graph. So you cannot just graph it on your calculator and just sort of eyeball what the curves are supposed to look like. And it might not be a bad idea to get yourself some colored pencils to, be able to show everything in different colors. Now, hopefully after doing number 5, you pretty well understand how to find the zeros and how to find the vertical asymptotes. But if you need more practice, you can pause the video at this point and you can give number 6 a try, and you can check it with the answers that I have up here as well as with the graph drawn. But I'm going to go ahead and move on to talk about horizontal asymptotes. So there are three scenarios that could occur with any rational function. Either it does not have a horizontal asymptote, for example, the last two that we looked at did not have horizontal asymptotes, or the horizontal asymptote is the line y equals 0, or the horizontal asymptote is the line y equals the leading coefficient of p dividing by the leading coefficient of q. So here are the three scenarios. Here's how you decide. If the degree of the top is bigger than the degree of the bottom, there is no horizontal asymptote. For example, in that last problem that we did, number 5, x squared plus 3x minus 4 over x plus 3, notice that the degree of the top is 2 and the bottom is 1. Top is bigger than bottom, so there is no horizontal asymptote. If the degree of the top is smaller than the degree of the bottom, then the horizontal asymptote is automatically y equals 0. So if, for example, if this had been reversed and it was x plus 3 over x squared plus 3x minus 4, then I would have known that my horizontal asymptote was y equals 0, and I would write it down and move on to the next part. The third scenario is that the top and the bottom have the same degree. For example, 2x squared plus 4x minus 7 over 3x squared minus 17. Both of these are degree 2, so the horizontal asymptote is the leading coefficient of the top divided by the leading coefficient of the bottom. So my horizontal asymptote for this one would be y equals 2/3. It might not be a bad idea to make yourself 3 note cards or something with these scenarios on them, because you are going to have to remember those when it comes test time. So let's look at number 7 here. For number 7, we're going to add on to what we did in number 5 and number 6. We want to find the zeros, we want to find the vertical asymptotes, but we also want to find the horizontal asymptotes and then draw the graph. So I'm going to start by factoring. The numerator cannot be factored. The denominator factors into x plus 1 times x minus 1. So they do not have any common factors. So I know that my come from the numerator only, so that would be x minus 2 equals 0, so I would have a 0 at x equals 2. So I'm going to put a point there. Then my vertical asymptotes are going to come from the denominator only. X plus 1 equals 0, x minus 1 equals 0. So I would have vertical asymptotes at x equals -1 and x equals +1. So I'm going to draw those real quick. And then lastly, the horizontal asymptote, if you compare the degrees, the top is smaller than the bottom. When the top is smaller than the bottom, if P is less than Q in terms of degree, then my horizontal asymptote is automatically y equals 0. So that would be right here. So I would be looking for all of these parts on your graph. And then to figure out what exactly it looks like, see all these asymptotes here, we're actually going to have 3 parts to our graph. You're going to have a part that's down here. On those sides of the asymptotes, we're going to have almost a parabolic shape. In between these 2 vertical asymptotes. And then we're going to have a third one that goes like this. And now you're probably thinking, Miss Brigman, you just crossed over that horizontal asymptote. You can't do that. That's not true. Horizontal asymptotes only apply to the very ends of the function. So I can cross it in the middle of my function, but what it means is as I look to the far left and to the far right, I'm not touching that horizontal asymptote. So there you go. You learned something right there, didn't you? All right. So I'm not going to take the time to do number 8 because it's so similar to number 7. But if you'd like to, you can pause the video and I will pop the answers up here to it and you can check yourself. Okay, so there's number 8. And now we're going to move on to the last part, which is holes in graphs. Holes are going to occur whenever you have a factor in both the numerator and the denominator of a function. And you can read through this and it'll explain it to you in more important words, but basically the point is if it's a factor in the numerator and the denominator, then it creates a hole. So for number 9 here, we're going to find the zeros, the asymptotes, and the holes for this function, and then we're going to graph it. So I'm going to start by factoring. That's what I will always do in every single one of these graphing problems. And when you factor this, you're going to notice that x minus 3 is a factor in the numerator and the denominator. So that is not a zero, that is not an asymptote, that's going to create a hole. So we'll get to that in just a minute. I can do my zeros using factors that are in the numerator only. So that would be x plus 3. So I have a 0 when x is equal to negative 3. So I'm going to go put that on my graph. I have a vertical asymptote in factors that are in the denominator only. I don't see a factor in the denominator that's only in the denominator because x minus 3 is also in the numerator. So that means we do not have any vertical asymptotes. And then for the horizontal asymptote, if you compare the degrees, the degree of the numerator is greater than the degree of the denominator. And when that happens, we also have no horizontal asymptote. So the only thing left are holes. So holes are at the common factor, which would be x minus 3. So I'm going to have a hole where x is equal to 3. Now that does not mean that at 3, 0, I just draw an open circle and I have a hole. I have to approximate where that y value probably is based on the way that the rest of my graph looks. So this is where you're definitely going to want to go to your graphing calculator, go to y equals, and you want to type your original function in, x squared minus 9 divided by, oops, I forgot my parentheses there, divided by x minus 3. And then press second table. What we want to do is we want to scroll through the table and notice that when we go to where x is 3, we have an error. That's because there's a hole there. But if you look close to it, when x is 2 and when x is 4, I'm at 5 and then I'm at 7. So if I was willing to make a bet, I would probably say that I have a hole at approximately 3, 6. So I'm going to draw a big open circle there. And I know it's really big, but I want my teacher to be able to see that it's right there. And then as for the way the graph should look, I'm going to go look at the graph of it on my calculator. And lo and behold, what is that? It's a straight line. Well, what in the world? So I'm going to go back here, and I'm a straight line, and I do know that it needs to go through the point negative 3, 0 from what I figured out earlier. So I have a straight line with a hole in it, and that's a graph of my rational function. You're probably wondering why. Well, think about it. Look up here when we factored it. If I was working this as a simplifying problem, x minus 3 would cancel out as a common factor, and so that reduces to just x plus 3. So that's the line x plus 3, except that I have a hole where that common factor is. How neat is that? Okay, so one last test problem for you. I want you to take a minute and do number 10 all the way through. Find the zeros, the vertical asymptotes, the horizontal asymptotes, the holes, and draw the graph. Okay, so this should be your finished product. When you factor f of x, it factors into x plus 3 times x minus 2 over x minus 2. So you'll notice that we do have a common factor of x minus 2, which is going to create our hole down here at x equals 2. The non-common factor in the numerator, x plus 3, is where we get our 0 from at x equals negative 3. Because I have no uncommon factors in the denominator, I don't have any vertical asymptotes. And because the degree of my numerator is greater than the degree of my denominator, I don't have any horizontal asymptotes. So I have a 0 at negative 3, and I have a hole at 2. And so I went to my table and I looked, and when x was 1, I was at 4, and when x was 3, I was at 6. So my best estimate is that I should have a hole at 2, 5. And then the graph is another straight line with a hole at 2, 5.